Rising above the desert sands of Dubai, the Burj Khalifa pierces the sky with an elegance and audacity few structures in history have ever achieved. At 828 meters, 2,717 feet tall, it is not merely the tallest building in the world. It is a testament to human ambition, engineering, brilliance, and the relentless desire to reach beyond limits. From the moment it was conceived, the Burj Khalifa symbolized more than height. It represented vision, innovation, and the audacity to dream on a monumental scale. To understand this iconic skyscraper, one must delve into its blueprint, the intricate marriage of architecture, engineering, materials, and human determination that turned what seemed impossible into reality. The vision, a skyline reimagined. The story of the Burj Khalifa begins in the early 2000s, at a time when Dubai was transforming itself from a regional hub into a global city known for tourism, commerce, and luxury. The government and developers sought more than just skyscrapers. They wanted a symbol of ambition, a structure that would instantly communicate the city's economic strength, technological prowess, and futuristic vision. The goal was to create a vertical landmark that would not only redefine Dubai's skyline but also establish the city as a world-class destination for business, leisure, and architectural innovation. To realize this audacious vision, MR Properties, one of the largest real estate developers in the Middle East, commissioned Adrian Smith, a principal at Skidmore, Owings and Merrill, the architectural firm behind some of the most iconic skyscrapers in the world. Smith and his team were tasked with designing a building that would break height records, push the limits of engineering, and create an icon capable of inspiring millions. From the outset, the design brief was clear. The Burj Khalifa had to be the tallest human-made structure ever built, while maintaining structural integrity, functional efficiency, and aesthetic elegance. Achieving such an unprecedented height required a revolutionary approach to architecture and structural engineering. Conventional skyscraper designs could not withstand the immense wind pressures, seismic forces, and material stresses that a building of nearly 1 kilometer would face. Engineers had to rethink vertical construction from the ground up, developing new materials, structural systems, and construction techniques. Concrete formulations had to be specially engineered to support extreme loads, withstand high temperatures, and remain workable for pumping to extraordinary heights. Steel and reinforced concrete were combined in innovative ways to create a core structure capable of resisting both lateral and vertical forces. Equally important was the integration of form and function. The building's Y-shaped footprint was chosen not only for its visual impact but also for its structural advantages, providing stability while maximizing natural light and views for in-day occupants. Aerodynamic setbacks and tapering reduced wind vortices that could sway the building, ensuring comfort and safety even at unprecedented heights. The facade, a shimmering combination of glass, aluminum, and steel, reflects the sun while giving the tower its sleek, futuristic appearance. From the very beginning, the Burj Khalifa was conceived as more than a skyscraper. It was a statement of human ambition and innovation. Every decision, from the structural core to the exterior cladding, reflected a commitment to pushing boundaries, marrying technology with design, and creating a monument that would inspire awe for generations. The project would ultimately redefine what is possible in architecture, engineering, and urban development, setting new standards for cities around the world. The architectural concept. Adrian Smith's architectural vision for the Burj Khalifa masterfully blends inspiration from Islamic design with cutting-edge engineering. One of the most striking influences came from the Hymenocallis flower, known for its radial symmetry and spiraling form. This natural inspiration informed the tower's triple-lobed footprint, arranged in a distinctive Y-shaped pattern. Far from being merely decorative, this design serves as the backbone of the building's structural stability, enabling it to soar to heights previously thought impossible. The Y-shaped plan offers multiple advantages. Functionally, it maximizes natural light and panoramic views for residents, hotel guests, and office occupants, giving the tower a sense of openness despite its enormous scale. Structurally, the three wings act like supportive arms, evenly distributing the enormous weight of the building and providing resistance to lateral wind forces, which become increasingly severe at extreme elevations. The wing's geometry creates a torsion-resistant structure, minimizing twisting or oscillation caused by gusts that can exceed 160 kilometers per hour near the top. As the tower ascends, each wing tapers gradually in a spiraling pattern, a design choice that is both elegant and practical. The tapering reduces wind vortex formation, a critical concern for super-tall skyscrapers, which are prone to oscillation and lateral sway. This spiral not only improves stability, but also gives the Burj Khalifa its signature sculpted silhouette, making it instantly recognizable against Dubai's skyline. Every setback and taper was carefully calculated using computational fluid dynamics and wind tunnel testing to ensure that the building would remain both safe and comfortable for occupants, even during high winds. The setbacks at multiple levels also serve a dual purpose. Architecturally, they create the building's graceful, stepped appearance, which echoes the tiered minarets of traditional Islamic architecture. Practically, they act as aerodynamic buffers, breaking up wind flow around the tower and reducing the formation of vortices that could destabilize the structure. By staggering the mass of the building as it rises, the design mitigates dangerous sway and ensures a more secure environment for those at the uppermost levels. In essence, the Burj Khalifa's design is a marriage of art and science. Its aesthetic elegance is inseparable from its engineering ingenuity. Every curve, taper, and setback serves multiple purposes, enhancing beauty, improving structural performance, and addressing environmental challenges. Adrian Smith's integration of natural motifs with modern engineering principles demonstrates that super-tall skyscrapers are not just feats of height, but of intelligent, holistic design that balances function, stability, and visual impact. The Burj Khalifa thus stands as both an architectural icon and a triumph of applied engineering. Engineering a vertical giant. Designing Burj Khalifa was a challenge that pushed engineering boundaries. The building's extreme height meant it would face unprecedented wind loads, gravitational forces, and seismic considerations. Engineers had to ensure stability while maximizing usable space, comfort, and safety. The solution came in the form of a buttressed core structural system. At its heart, Burj Khalifa has a hexagonal central core that houses elevators, stairwells, and mechanical systems. This core is supported by 3 wings, creating a Y-shaped configuration that distributes weight and resists lateral forces. The buttressed core acts like the spine of the building. It provides rigidity, stability, and balance, allowing the skyscraper to reach unprecedented heights without succumbing to wind-induced sway. Engineers employed computational fluid dynamics simulations to model wind behavior around the tower, refining the shape and setbacks to minimize vortex shedding and vibrations. The foundations are equally impressive. Burj Khalifa rests on a massive reinforced concrete mat, over 3.7 meters thick, supported by over 192 piles drilled into the bedrock, each extending more than 50 meters deep. This foundation distributes the enormous weight of the building over 500,000 tons and ensures stability on Dubai's sandy soil. Materials and construction. Constructing the Burj Khalifa required not only groundbreaking engineering but also meticulous attention to materials and their performance under extreme conditions. At its core, the tower relies on high-performance reinforced concrete, chosen for its exceptional strength, durability, and ability to withstand the immense compressive and tensile forces generated by such a tall structure. The reinforced concrete forms the building's buttressed core and wing support system, providing stability while allowing the structure to taper elegantly as it rises. The exterior facade combines reflective glass, anodized aluminum, and stainless steel, creating a striking, modern aesthetic while offering resilience against Dubai's harsh desert climate. These materials were selected to resist extreme heat, intense sunlight, sand abrasion, and high winds. The glass panels, carefully treated and coated, reflect solar radiation to reduce interior heat gain, improving energy efficiency for a building of this scale. Aluminum and stainless steel elements not only provide structural support and finishing durability, but also contribute to the tower's sleek, shimmering appearance that has become a defining feature of the Dubai skyline. One of the most remarkable challenges in the construction process was pumping concrete to unprecedented heights. Standard concrete mixes would set too quickly, so engineers developed specialized formulations with retarders and other additives to maintain workability during transport. Custom high-pressure pumps were employed to push concrete over 600 meters vertically, marking one of the tallest concrete pumping operations ever attempted. This required careful coordination, precise timing, and rigorous quality control to ensure the integrity and strength of every floor as the tower ascended. Steel played a strategic role in the tower's spire, which extends an additional 200 meters above the main structure, enabling the Burj Khalifa to achieve its record-breaking height of 828 meters. The spire's steel framework was designed to withstand extreme wind forces while maintaining minimal weight, allowing the concrete core below to bear the primary structural load. Every component of the spire, from steel beams to cladding panels, was meticulously engineered to endure thermal expansion, desert winds, and ultraviolet radiation without compromising stability or aesthetics. Even the curtain wall system was optimized for performance. The glass panels are mounted with precision to allow slight movement under wind loads and thermal expansion, while maintaining a continuous weatherproof envelope. Aluminum mullions provide additional rigidity and anchor the panels securely to the reinforced concrete structure. Collectively, the choice and application of materials in the Burj Khalifa reflect a symphony of engineering precision, where every element, concrete, steel, glass, and aluminum, works in harmony to create a resilient, elegant, and enduring architectural icon that continues to push the boundaries of what is possible in super-tall skyscraper construction. Elevators and vertical transportation. One of the most remarkable yet often overlooked engineering achievements of the Burj Khalifa is its vertical transportation system. The tower features 57 high-speed elevators and 8 escalators, designed to serve the enormous vertical span of 828 meters across 163 habitable floors. Among these, some elevators are the fastest in the world, reaching speeds of up to 10 meters per second, allowing passengers to ascend from the ground level to observation decks or residential floors in mere seconds, a feat unimaginable in conventional high-rise buildings. Designing elevators for such extreme heights presented unique challenges. Standard elevator systems could not withstand the combined effects of wind pressure, air turbulence, and cable tension encountered over nearly a kilometer of vertical travel. Engineers had to develop reinforced, high-tensile cables and aerodynamic elevator cabins to reduce sway caused by wind forces. The shafts themselves were carefully aligned and reinforced to maintain smooth, reliable operation even under gusty conditions, ensuring passenger safety and system longevity. A key innovation in the tower is the double-deck elevator system, which allows 2 cabins to operate simultaneously, one atop the other, effectively doubling capacity without increasing shaft space. This design was critical for efficiently transporting thousands of residents, office workers, hotel guests, and tourists throughout the building. The system is integrated with intelligent dispatching algorithms, which optimize elevator assignments based on demand patterns, reducing wait times and energy consumption, while maintaining seamless traffic flow in a building where a single elevator ride could otherwise take several minutes. Comfort was as important as speed. Riding an elevator nearly a kilometer high can expose passengers to air pressure changes, vibration, and the sensation of rapid vertical motion. Engineers implemented sophisticated cabin suspension, dampening systems, and pressurization controls to minimize these effects, ensuring a smooth, almost imperceptible ride. Noise was also reduced through precision engineering of guide rails, motors, and counterweight systems, providing a quiet environment despite the elevator's high speeds. The escalators, although less publicized, also contribute to the tower's efficiency, particularly in public areas such as lobbies and shopping zones. They are carefully integrated with the elevator system to facilitate pedestrian flow, reducing congestion and complementing the vertical transport network. Together, the escalators of Burj Khalifa represent a masterclass in vertical mobility engineering. They demonstrate how human ingenuity can overcome the limitations of height, gravity, and wind, transforming what could have been a logistical nightmare into a seamless, efficient, and comfortable experience. In many ways, the tower's vertical transportation system is as iconic and groundbreaking as its soaring concrete and steel structure, making it not just a skyscraper, but a marvel of integrated engineering design. Sustainability and environmental considerations. Despite its record-breaking height and iconic presence, the Burj Khalifa was designed with a strong emphasis on sustainability and environmental responsibility. The architects and engineers recognized that a building of this scale could have a massive ecological footprint, so they integrated systems and strategies to conserve resources, reduce energy consumption, and adapt to Dubai's harsh desert climate. Sustainability was not an afterthought, it was a core aspect of the design philosophy. One of the most innovative features is the condensate recovery system. The building's air conditioning units generate enormous amounts of water through condensation, which is typically discarded in conventional systems. At Burj Khalifa, this water is collected and repurposed for irrigating the extensive landscaping around the tower, including gardens, fountains, and palm-lined plazas. This approach reduces reliance on potable water, a critical consideration in a region where water is scarce and expensive. The glass curtain wall system also contributes significantly to energy efficiency. Composed of reflective glazing, aluminum panels, and thermal insulation, the facade reduces solar heat gain, preventing excess heat from penetrating the interior. This lowers the demand on the building's air conditioning systems, which would otherwise consume enormous amounts of electricity to maintain comfortable indoor temperatures. The windows are carefully angled and coated to balance natural daylight with thermal performance, creating a bright interior environment without compromising energy efficiency. Lighting and electrical systems were designed with similar principles in mind. High-efficiency LED lighting, motion sensors, and intelligent controls minimize unnecessary energy use, while the building's centralized control system monitors consumption in real time, allowing operators to optimize performance. Heating, ventilation, and air conditioning (HVAC) systems are also tailored for energy conservation, with zone controls and variable speed pumps that adjust to occupancy levels and outdoor conditions. Even the building's shape contributes to sustainability. The tapering, spiraling design reduces wind loads and mitigates thermal exposure, lessening the structural stress and cooling requirements. By combining architectural form with environmental function, Burj Khalifa demonstrates that aesthetics and sustainability can coexist even at extreme scales. Through these innovations, Burj Khalifa serves as a blueprint for responsible megastructure design, proving that environmental considerations are not incompatible with ambition. The tower exemplifies how engineering, architecture, and ecological awareness can be integrated to create a structure that is not only awe-inspiring but also mindful of its environmental impact, setting a precedent for future skyscrapers around the world. Interior design and functionality. Burj Khalifa is not just a record-breaking structure, it is a multifunctional skyscraper. It houses residential apartments, corporate suites, luxury hotels, observation decks, restaurants, and mechanical floors. The interiors were designed to complement the tower's external elegance while providing comfort and luxury. From marble floors to advanced HVAC systems, every detail reflects meticulous planning and world-class design standards. The observation decks, on the plan, 124th and 148th floors, offer breathtaking panoramic views of Dubai, providing not only a tourist attraction, but also a demonstration of human achievement and engineering mastery. Safety and resilience. Safety was paramount in a building of this scale. The design accounts for extreme wind, seismic activity, and potential fire hazards. Multiple stairwells, refuge areas, and pressurized evacuation routes ensure occupant safety. Fire-resistant materials, advanced sprinkler systems, and smoke evacuation systems were integrated throughout the building. Structural redundancy ensures that even if one component fails, the building maintains stability. Engineering a skyscraper of this magnitude required foresight and contingency planning on a scale rarely seen in architecture. Every floor, column, and connection was tested against worst-case scenarios to ensure resilience and longevity. Cultural and economic impact. Since its completion in 2010, Burj Khalifa has become a global icon. It transformed Dubai's skyline, attracting millions of tourists and inspiring international admiration. The building has appeared in films, commercials, and media worldwide, cementing its status as a symbol of ambition and modernity. Economically, Burj Khalifa catalyzed urban development in Dubai. Its presence attracted businesses, residents, and tourism, contributing significantly to the city's global reputation. Beyond economics, it stands as a cultural landmark, a testament to what can be achieved when vision meets engineering excellence. Lessons from Burj Khalifa. The Burj Khalifa is more than a record-breaking structure. It is a blueprint for innovation and achievement. Visionary thinking. The project demonstrates the importance of bold ideas and long-term goals. Engineering excellence. Advanced structural systems, materials, and construction techniques push the limits of possibility. Integration of form and function. Architectural elegance harmonizes with practical stability and resilience. Innovation. Under constraints. Overcoming wind, heat, seismic activity, and soil challenges required creative problem solving. Sustainability and responsibility. Environmental and safety considerations show that ambition and responsibility can coexist. These lessons extend beyond skyscraper construction, offering inspiration for engineers, architects, and innovators in all fields. The legacy of a giant Burj Khalifa is not merely the tallest building in the world. It is a symbol of human aspiration, perseverance, and achievement. Its blueprint from foundation to spire illustrates the power of imagination combined with precision engineering. The tower demonstrates that constraints are opportunities, not obstacles. The desert landscape, wind, and seismic considerations became challenges that shaped the building's design rather than limiting it. It also reminds us that engineering is not just about functionality, it is about creating experiences. The Burj Khalifa inspires awe, challenges assumptions, and pushes humans to reimagine what is possible. For decades to come, it will serve as both a tourist attraction and a technical reference, influencing architects, engineers, and visionaries around the globe. The Burj Khalifa stands as a vertical monument to ambition, innovation, and human creativity. Every floor, column, and spire is a testament to meticulous planning, advanced engineering, and bold vision. It is more than steel, glass, and concrete. It is a blueprint for what humans can achieve when imagination meets determination. From the foundation deep beneath the desert sands to the pinnacle that pierces the sky, the Burj Khalifa is a living testament to our capacity to dream, to design, and to build beyond the limits of possibility. In a world constantly reaching higher literally and figuratively, Burj Khalifa reminds us that with vision, courage, and innovation, no height is unattainable. It is the tallest skyscraper in the world. But more importantly, it is the tallest symbol of human potential.